We're completely open. Also, we look into all kinds of aircraft configurations. There is this tube and wing called classical aircraft design as we know it, and non-aeronautics experts sometimes blame us for not being creative and always stay with the same. Actually, we don't stay with the same. We look into all kinds of configuration you can imagine of, also flying wings and whatever. But physics always bring us back to the designs which we have. So it's not the reason that we didn't look into others. It's just the beauty of the physical beauty of the solutions we have today, which bring back these again.
Hamburg Aviation Green.
Welcome everyone to the first show in our second season of Hamburg Aviation Green, the show where we explore some of the stories and meet the people, discuss the technologies and the challenges ahead for sustainable aviation made in Hamburg. My name is Angus Bagent.
And I'm Carolina Oxley. This week, for our very first episode of the second season, we want to do a deep dive into the holistic approach of green aviation. Often when we talk about green flying, we look at one specific technology. But we want to widen the look today and find out how is everything interconnected.
And that's exactly the kind of approach that Björn Nagel's institute at the German Aerospace Center is working on and is actively researching. So welcome Björn Nagel, you're director of the Institute for System Architectures in Aeronautics. Welcome to the podcast.
Yeah, many thanks for having me here.
Before we dive in, can you give our listeners a little overview, like what are you doing at your research center and what are the most important projects right now?
Yeah, maybe first of all, would be good to quickly introduce DLR, because surprisingly many people do not know what this is. It's actually the National Research Center for Aeronautics and Astronautics, obviously, but we are doing also research in transport and energy. And we are quite large. We have 54 scientific institutes dedicated to different disciplines. We have about 11,000 employees and 30 sites all across over Germany. So actually, we are worldwide the second largest organization of our kind, just second to the NASA in the United States. And maybe briefly, what is a large-scale research center and what's the difference to a university? The universities were there before, but at a certain time we found that actually we need application-close research, which requires large experiments, also large and also expensive infrastructure like wind tunnels. Actually, DLR was founded already in 1907, or the antecessor organizations of DLR.
Wow, really? 1907? Oh.
Yeah, in Göttingen, and it started all with a wind tunnel.
That's way before NASA. I think NASA was founded in the 50s or something.
We're quite old. Though in Hamburg, we are quite young. Okay. We'll come to that in a minute.
Yeah.
But so the fundamental idea was that we need large and expensive experiments, what is beyond a university can afford. Also today, the university are funded by the states of Germany, and large-scale research centers are funded by the federal government. So we have for all Germany, so this is also the reason why we are spread all over Germany. And we are bridging the gap between the fundamental research at the universities, where it's okay to have experiments at a certain scale. But if we want to have a wind tunnel where we have large experiments, we have research aircraft up to an A320, what we are using for this is on the large-scale research as we are doing this. And next to these substantial experiments, there is a second aspect which comes new and also comes back to the introduction. Actually, with our 54 institutes, we cover all aspects of aviation. At a high level of details in each discipline, we have these experiments, but it's also relevant as aviation is actually very interlinked or highly integrated. We also need to resolve all these interdisciplinary aspects. So what's in between aerodynamics and structures and propulsion and all these things. And so we have these large experiments, but we're also quite complete in the disciplines. And when you have an interdisciplinary question, DLR is that organization which brings all this together. And what we're doing here in Hamburg, actually, I'm director of the Institute of System Architectures Aeronautics. We were founded exactly 110 years after the roots started of DLR. And we were funded exactly for the second aspect. So we have all these research institutes which develop technologies, but also simulation models for the different disciplines. And our institute aims at the scientific questions: how can we bring all this together? How can we find solution for aviation as a whole, where all these different technologies get into play? And there are two main questions we have to answer. One of them, what's the architecture for aircraft? How do we combine the technologies? And the second question is, how do we make use of all the simulation capabilities? So to imagine a future solution for aircraft is one thing, but then also to do the computations and come with the numbers, that's the second aspect. And we're doing this not alone, but by making use of all the competence and capabilities we have at DLR. So we are an institute which highly interacts with all the other institutes of DLR.
Do you also interact with industry? We'll talk about the Center for Applied Aeronautical Research in a minute, where you're housed. But you also work with industry to some extent as well?
Yeah, actually, this is the reason why DLR came to Hamburg some years ago, actually. So we have a long record of research in the different disciplines, and if you know the DLR sites, they're quite often somewhere in a forest where you don't disturb anybody if you have a loud experiment or whatever. We're quite good in doing these experiments. We have also the experiments, we have the research there. But now it's very important to do the research in an application-oriented way. In particular now, as it's a bit uncertain how the future of aviation will look like, we need to have a quite close dialogue with industry to exchange about the vision. How might aviation look like? What kind of aircraft can we expect? Also meaning what kind of aerodynamics do we need? What kind of structures and all this? And this is actually what we're doing here in Hamburg. So we have the physical competences still spread over Germany. But here in Hamburg, we are in close dialogue with Airbus, with Lufthansa Technik on MRO and all these things.
Fantastic. I mean, that's something that's quite unique in our particular setup. There's one project that I know that your institute has taken the lead on. That's the EXACT project, which I think that's been running for 2 years. Would you like to give us a quick overview of EXACT and what the aims are of the project and who you're working with?
Yeah, actually, we started the planning of EXACT already, I think, 6 years ago, and the first EXACT project has already been completed after 4 years now. The question we want to answer is, which is the best technology pathway towards climate-neutral aviation? So there's so many technological options on the table, and also so many combinations how to bring this together, like a laminar wing, open rotor, or hydrogen as propulsion batteries and all this. And we needed to find out actually, which are the best technologies. And what is quite unique to this project, actually, that is we really want to make use of all the capabilities we have, not digging deep into the disciplines, but really being able to look at this from end to end over the entire life cycle of the aircraft, but also of the energy carriers. So we brought together about 165 scientists from 20 of our institutes, investing quite a high amount of resources also into this. And first we established a simulation capability, really starting with the production of the energy carrier. So where on this planet can we get green energy? We already know Germany will need to import energy, so this source needs to be somewhere else.
Right, that's going to be clear already, absolutely.
Yeah, so we have an Institute for Networked Energy Systems, which is really focusing on this, and they made studies for 12 reference airports all around the globe, and they investigated where would they get the energy from, usually from the sunbelt of the planet, and then there are different ways. First you have electricity. You can produce hydrogen out of this and directly transport this. It's quite difficult to transport hydrogen. You could also process it further, create PTL, which is easier to transport, but more energy demanding to produce. And then for all these 12 reference airports, they compared what would it mean and what would be the total energy demand to provide a certain amount of energy over the different energy carriers. So this was only the first beginning of the EXACT analysis chain. Then, of course, we compared all kinds of propulsion technologies, so hydrogen propulsion with fuel cells, with direct burn, with SAF. Of course, for all propulsion options, it's always important to be energy efficient with the aircraft. So, of course, what is now new and relevant are the new propulsion concepts and energy concepts, but all the the classical disciplines like for energy efficient flying, so low drag, low weight, all this is even more relevant than the past. It's a bit forgotten in the public discussion actually, but of course we look into many of these technology as well and looked into what kind of aircraft concepts can we produce, and then how do we operate them, and to the question, what's the climate impact? And climate impact is a bit more than only CO2 emissions. So all this, how to operate aircraft, what does it mean? So we established the entire chain. And then actually we were quite open in terms of technologies. Actually, we looked into all technologies which can be imagined for propelling an aircraft, how to design an aircraft. And then over the time, we were narrowing down and see which are the most promising solutions. And then we iteratively increase the level of fidelity, because of course in the beginning, when you're very wide, you need to be very fast, which is low fidelity. And after pre-selecting, we get the next higher level of fidelity simulations, and like this we go down the line.
I was just going to ask, with fidelity, you mean the granularity or the detail level in the simulations you're talking about, right?
Yeah, how precisely you resolve the physical effects. So if you start a first conceptual aircraft design, you can have very simple assumptions about what's the weight of an aircraft. But like if you have an aircraft with a hydrogen tank, of course you cannot use any empirical estimations, but then you need a physical simulation. But we started with first estimating these kind of things and then getting more and more complex simulation models, which are more precise, but also require more and more time and effort to do this.
We also talked a little bit in preparation for today, and I was very surprised that actually there were some very interesting and perhaps not expected results of the exact project. Just to pick up on electric and also hydrogen, you know, there's a received wisdom, electric only, very short range, regional, very short, and hydrogen absolutely not feasible on long haul at all. But that's not necessarily what the results of the exact project are, right? Do you want to tell us a little bit more about that?
Yeah, this is very interesting, this project, because we are quite often surprised by the results from the computations, because when we started exact, actually the E in the name from exact means electric. This was like 5 or more years before. People thought that electric flight would be the future. And then quite early we found out that batteries are quite heavy. So then we thought, okay, it's a bit annoying that we have the E of exact in our name, because electricity does not play such a role, because obviously batteries are too heavy to be used in a large transport aircraft. But then we really dived deeper into all this and also looked into how our aircraft actually operated. In exact, we are concentrating on aircraft which should not be smaller than 50 passengers to have an impact, but also not larger than medium-sized aircraft, because we believe this will be the next generation of aircraft which will be produced and designed. And if you look into today's operations, these aircraft are capable of doing quite long ranges, but very often they're operated only at 500 kilometers. And this would be a range you can operate with batteries as well. And when we started our studies, we more looked at the design range, which is far more than that. And we don't have a chance to really have the very long distances of this kind of aircraft using battery electric flight. But being aware that actually the majority of operations is a very short routes, which can be operated using batteries, we found that actually is a quite very good solution to have a hybrid electric aircraft, where on short distances up to something like 500 kilometers, we can fly battery electric. And then we have an excellent energy efficiency. So charging, decharging batteries and electric motors is very efficient compared to producing hydrogen or even worse, PTL. But of course, this only works for the short ranges. But as they are kind of dominating the operations, it's a quite good solution. And for the very few routes we have which are beyond this, we still have a combustion engine, which then is used with sustainable aviation fuels. This is not as energy efficient as the batteries, but it's only the solution for the few long ranges which are operated in this range.
That's fascinating. Yeah, so you're looking actually at the use cases, how long are the flights, and not just comparing the aircraft and what the ranges are of the actual aircraft. That's fascinating. So Björn, something that in these various discussions in our industry that's often talked about is the different development paths, the different technologies. Is it going to be this? Is it going to be that? What is your take on SAF compared to hydrogen, compared to electric or mixed models and hybrid technologies? What's the philosophy of your institute?
Actually, it's a bit twofold. One would be the medium to long-term solution. There we need to find out which is that way which will enable greener and more energy efficient air transport. The other question is, how do we get from today to this medium to long-term future? And there it's clear that there are many aircraft which are flying, which are still in good conditions for many years. And to power them, we will need sustainable aviation fuels. So we will need SAF for sure. The question is if and when we will be able to also add hydrogen and enable the higher energy efficiency of that energy carrier or not.
I think it's fascinating also to, like in Germany, for example, when the federal government talks about SAF, they're talking about PTL. That's for them the preferred long-term view. But like you were saying, there's for that of course we need hydrogen. There needs to be strong domestic production or imports as well. What do you see as the short-term challenges in terms of scaling up production, regulatory issues, and also feedstock sourcing? How do you think we should approach those kinds of issues?
Well, in terms of feedstock, there are some good feedstocks available to produce biomass to liquid, like used frying oil. It's an excellent source to efficiently produce BTL. But there is not that much frying oil available, and other feedstocks might be less efficient for the production. So we believe that there is a certain potential for BTL, but it's quite limited. And at larger scale, it needs to be energy-based. So first we need to produce hydrogen and then either directly use it after liquefying or to process it then to PTL. I think the biggest challenge actually is how can we attract investors to get this started? Looking at the globe as a whole, there are great opportunities to generate green energy, mainly using solar cells in the sunbelt of the planet. This can be very economical to do that. The problem is only that currently there is not a customer to that, and this is why investors do not build up this infrastructure and offer this. So another chicken and egg problem. And when it comes also to the production of PTL, the production technologies for PTL are relatively young and not very mature yet. So the first ever production facility at industrial scale is just being established by DLR actually. But if you're an investor, there is not really a customer to the product. And if you wait a couple of years, you will have a better infrastructure you can buy and have a higher revenue, a higher efficiency of everything. This lets you wait as an investor. And how can we attract investors to now invest into these technologies and make the energy available? I think this is currently the biggest challenge we have.
Yeah, absolutely crucial. I mean, if we look at we're already in a situation where we know how much we have to produce because the EU has mandated, has got blending mandates in place, 2026, 2%. And that's, and I was reading some research the other day that even the currently pledged infrastructure that we have now is going to deliver maximum half that. So the question is how can we scale up quickly? I guess from our point of view, I suppose building the consensus between fuel suppliers, aviation, the public sector, private sector. There's probably a lot of connections that need to be built and a lot of networks that need to be harnessed for that to happen.
Yeah, I fully agree.
You also looked at hydrogen and had a look at what ranges hydrogen aircraft could be feasible in the future. And you had a couple of surprises for us there too.
Yeah, actually, hydrogen requires a much more volume compared to kerosene. And if you go for long-range aircraft, then there is a lot of fuel volume you need. And if this is 4 times more than before, we always believed that just we cannot accommodate all this energy in the aircraft. And so we also started a project on long-range aircraft operations, particularly looking also on these non-CO₂ effects. In the course of this project, we also wanted to compute how a hydrogen aircraft would perform in long-range conditions, actually only expecting to give the proof that it does not work. So we are not hydrogen addicts and want to push it everywhere. Actually, we wanted to demonstrate that it does not work, a bit like with the batteries on the medium range. It was the same kind of story. But then we framed the problem wide enough. Actually, we did not only look at an existing aircraft and only stretch the fuselage, but we looked what's the problem. So, and for these large tanks, also the mass of the tank is an issue. But the mass is also driven by the shape of the tank. If you have a long-range aircraft, it's a very lengthy tank you have. And we found if the tank is more circular, like a ball, the weight goes down quite a lot. So we modified the fuselage from a standard twin-aisle fuselage to an ultra-wide fuselage with 3 aisles in the cabin, which is a challenge for cabin design. Mm-hmm. But if you accept that you have this very wide diameter of the fuselage, you can have way lighter tanks, have a shorter fuselage, so less problems with weight and balance. And so we found actually a solution that if you're open enough to go for a very wide fuselage, which still looks like a conventional aircraft, only if you look into the details of the cabin, you see that it's quite revolutionary, but still this small change to the design enabled a solution where actually also on long range hydrogen is feasible.
That's
that's fascinating. So am I right to be able to fly with hydrogen, you need to redesign the entire aircraft, like including the interior, to fit these new tanks? Like, so you're looking at into new designs, I assume, for aircrafts. Is there anything already out there that's maybe recognized by the wider community?
Yeah, we're completely open. Also, we look into all kinds of aircraft configurations. There is this tube and wing called classical aircraft design as we know it, and non-aeronautics experts sometimes blame us for not being creative and always stay with the same. Actually, we don't stay with the same. We look into all kinds of configuration you can imagine of, also flying wings and whatever. But physics always bring us back to the designs which we have. So it's not the reason that we didn't look into others. It's just the beauty of the physical beauty of the solutions we have today, which bring back these again. We also looked, of course, can we have a retrofit of existing aircraft with hydrogen tanks? And usually we can't. Actually, there is a lot of volume the tanks need, and also quite a lot of mass which is needed. And it is not possible to retrofit this efficiently into existing aircraft. The most efficient way to integrate hydrogen tanks is the one which also looks sometimes a bit boring. It's just behind the passenger cabin, just have 2 hydrogen tanks, which are like balls, and fill kind of the entire fuselage. Need to be 2 tanks for redundancy. And the more ball-like the tanks are shaped, the better it is in terms of weight. This is why we always come to the solution. It's also the apparently easiest thing, but it's actually the best one. If we have tanks in the rear, there's a lot of weight in the rear, which usually is not there for conventional aircraft. So if we would just take a conventional Airbus A320, move the rear bulkhead to the front, make the passenger cabin smaller, and have the tanks in the rear, then there would be too much mass in the rear, and it would not work with the old design. If from the beginning we know that we will have heavy tanks in the rear, no problem, and we can just put the wing and the landing gear to positions that it works. But we need this degrees of freedom that we move the wing forth and back, and this means we need an entire new aircraft.
So the regular passenger wouldn't even be able to tell this is I'm flying with hydrogen because everything is like it used to be.
Exactly.
Yeah.
I mean, we definitely want to come back to digital engineering, digital tools, because I'm absolutely certain that that takes a lot of accurate modeling, and you need to construct the right models to be able to draw a lot of those conclusions. I just want to talk briefly with you about hydrogen. I mean, hydrogen's a topic and a technology that a lot is going on in Hamburg. The airport is working on implementing hydrogen. How can they build the right infrastructure? The city is developing hydrogen. I think there's a total of 600, including federal funding, over 600 million euros being spent in Hamburg in the region. Airbus, of course, some of the zero-E work on that project is also happening in Hamburg. So, and then you're also doing a lot of hydrogen research. So, yeah. Why is so much impetus or so much dynamics happening in Hamburg around this particular topic?
Actually, hydrogen is not new. Also in space, for rockets, this is very conventional fuel for rockets. We know how to deal with this. And also in the chemical industry, hydrogen is we're used to use it. So in principle, we know it. So in stationary applications, usually hydrogen infrastructure is extremely heavy. So it's very difficult to contain the hydrogen in the tank, and also if it's cryogenic, it needs to be isolated. If you have a stationary application and weight does not matter, you just have a massive structure. And no problem to operate this. If you have a rocket, weight is a driver, but you only use it once, and the hydrogen is only very short time in the tank. And we have good experience in both applications, but an aircraft is sometimes in between of these two. And so we know not enough about hydrogen that we can create something that is safe. So no doubt about creating that. But the question is, how light can we be for something that is more often used than just one time and a few minutes? And this is what we need to find out, actually, which are the design principles we need to apply to this kind of vehicles and also ground infrastructure for the specific requirements of aviation. And there are multiple types of requirements to this. Flight physics is maybe the most obvious, weight of the tank and the volumes. But maybe the biggest question might be, what about maintenance, repair, and overhaul? So we have hydrogen in cryogenic state in the aircraft. So there's a very big challenge for all kinds of materials. And what does it mean? Do we need to replace the hydrogen tank? Likely, yes. This will be very, very expensive, of course. But how often does it need to take place during the aircraft's life? What about all the supply lines in the aircraft, but also in the airport? And we have a typical chicken and the egg type of problem. So we do not have a hydrogen aircraft. This is why we cannot make any experience. Because we don't have any experience with hydrogen aviation, we don't know how to design a hydrogen aircraft. And and this is, we are breaking this chicken egg circle, for example, with the Hydrogen Aviation Lab, as you mentioned this, by just using an Airbus A320, which has reached the end of its service life in the Lufthansa fleet. It's not only a ground demonstrator, but we simply is not the right word, but we just put a fuel cell and a liquid hydrogen system in this aircraft, not with the intent to fly it, but to operate it on the airport and really to learn how it works. And the airport is involved. If you want to use liquid hydrogen at an airport, not necessarily each airport is super happy with your idea that you will start this off. We're happy that we have this particular airport here in Hamburg, which is anyway very pushing towards green aviation and green operations themselves. You need a company like Lufthansa Technik doing the MRO competence. And we have here in Hamburg, of course, also the manufacturer Airbus. There's multiple projects with them as well. So we can look into all the different aspects of hydrogen. And you already mentioned also the supply of hydrogen. So we will need to import energy as a nation, and the port of Hamburg would be the port in Germany where energy will reach us. And this is why Hamburg also has this fantastic opportunity to have a real world or living lab, and we can really experiment how to get the hydrogen or different sources of energy to Hamburg, how to distribute it, how to bring it to the airport, into the aircraft. And so we have everything here together. And I think this is why Hamburg is a perfect spot really to look into this kind of holistic problems, actually.
Right. Yeah, fantastic. That's fascinating. I mean, but you sometimes you probably have this also when you're in international conferences, and I mean this is something we're working on in Hamburg, and we're also extending networks. Airbus and also our Hamburg Airport is also working on developing networks to pool resources, pool expertise, because of course we need a network of airports that are going to be able to refuel the hydrogen aircraft and so on. What do you think, from your experience? When we look internationally, how are other regions looking at hydrogen? Are they more skeptical, or are they open to it, to working perhaps with us in Hamburg to develop new solutions?
Yeah, I think in Europe there are also other regions which have similar interest and also see that high potential in hydrogen, like also in the Netherlands. You see this, and also in France initiatives.
We're also working on we're hoping to establish by 2026 the first regular hydrogen flight route between two airports, between Hamburg Airport and Rotterdam. That's another project that we're also working on here.
I think this kind of project are really key to demonstrate that there can be a network. It's not only Hamburg which has an interest in hydrogen, that there are multiple regions, and we can demonstrate flight. Also, it's essential to not only make experience with an aircraft on the ground, but also have first roads where we can operate aircraft and really experiment on that. Looking more on a global scale, actually in the United States, they see a higher potential in sustainable aviation fuels, actually, because also they believe that there is a lot of biomaterial which can be used to generate biomass to liquid SAF, which might be quite efficient, but there are a bit different estimates on how much biomass is available. In the United States, we have a lot of biomass, and we also have a lot of waste which might be used to produce SAF. In Europe, actually, we try to avoid waste, so there's not that much waste potential for BTL production. And also we believe that we want to move towards sustainable agriculture as well, so less intense farming. And so going for biomass is not a good solution, in particular not if we want to scale up beyond the current state of the art. And that's a bit the difference between US and quite often it is used as a kind of a killer argument against hydrogen. So if the United States, if they would go for sustainable aviation fuels, so for synthetic kerosene, and only we go for hydrogen, that's not enough. Actually, from the studies we did in the exact project, we see that actually there is a huge advantage of hydrogen compared to power to liquid SAF in terms of energy demand. Actually, you need about 50% more energy to produce and distribute PTL compared to liquid hydrogen. So there's a huge potential for hydrogen, which we're quite sure that it is there. If it's exactly 50%, it's many assumptions in these studies, but it's significant. What we see. And we looked at the different side of the world, like Japan. They've just released their aeronautics strategy, and they actually also look a lot into SAF, but also a lot into hydrogen. Japan wants to concentrate also on do the transfer from automotive applications. They had a lot of experience also with ground-based fuel cell systems to aviation. And just in the beginning of the year, actually, it was in the press that China made its maiden flight of a 4-seated research aircraft, which was hydrogen-powered. And we were also quite interested in this because from the gut feeling or what we know from the past, we always believe that China is only looking at the best economic solution. But actually, from a dialogue just last week, actually, we learned that they really focus on hydrogen as the energy carrier for the future, because they have a very holistic view about their system. It's politically very different. And so the Chinese government knows that they do not want to use their land for the production of plants for fuel. They need it for the production of food. It's very clear on that side. So there is no BTL solution seen. And if you have to produce your fuel energy based, then it is straightforward. Also what we found out that actually hydrogen is far more energy efficient. And what's simple in China, of course, the China's government can decide that the airports will have hydrogen, there will be a hydrogen aircraft, and the airlines have to use it. So all the question mark we had, whether will there be a hydrogen ecosystem around, will the airlines accept this, will the airports accept them, that's quite simple over there. And yeah, it's exciting to see. They are several years behind what we're doing here in Europe, but they are straight moving to that direction. And that brings also quite interesting perspective also now on the strategic decision whether we proceed with SAF or with hydrogen. Sometimes it appears to be simpler to go for SAF, at least from the aeronautics sector. Someone else needs to provide the fuel, but it's of course straightforward to have an SAF aircraft. But what if we go for SAF and the Chinese continue with hydrogen, and then they might take the lead in this technology.
That's really interesting. Like if you, looking at Asia and looking at time frames, I think most industry partners are aiming for 2050 to fully decarbonize. So there is still a lot to be done. So the question is, can we get there fast enough?
That's a question I get quite often. So isn't it far too late, and isn't it that we never have a chance to do this in time? I think it's a situation like when the United States was said in 10 years we want to fly to the moon and then bring a human to the moon. Also at that time when people were asked, it's not feasible, we've never brought a person to the moon. I think it's like this. I think it is feasible, but it is extremely challenging, and for sure it is not easily done, or we cannot be sure that it's done, but it is possible. And the optimism I have here is because I think for the first time we can really deploy digital engineering at large scales. We have all these large scale activities like the Hydrogen Aviation Lab. We're learning about how to operate hydrogen systems, and we are in parallel to the physical experiment. We have a digital twin of the Hydrogen Aviation Lab. And so from the experiments, we transfer the knowledge into the digital models, which we can then use to design the next aircraft. So when we design an aircraft, we can already make use from the knowledge for that. We do all the flight experiments, and that's the same. So we do multiple large-scale experiments into different aspects of the next generation of aircraft, and we have large-scale simulation models, and for the first time we will be able to really integrate them and have a fully multidisciplinary design, not only covering flight physics, but also operations and also the manufacturing of the aircraft and the factory on the future, as we're developing it here in Finkenwerder.
You just mentioned just Finkenwerder, and I just wanted to ask you, in terms of your institute, I mean, this year you moved to new offices or new facilities at the ZAL, the Center for Applied Aeronautical Research here in Hamburg. Tell us a little bit about the ZAL and why that is a facility that supports your work.
Yeah, like I already said earlier, Hamburg is a place for aviation because we have all stakeholders of aviation. So we have the manufacturer, we have operators, we have MRO, we have research, we have academia. And the ZAL actually is the innovation hub where all these players get together. So it's an infrastructure, and everybody who wants to do research in aviation can just rent some space without doing own investments. So it's relatively easy to move in and be there. And then there's actually two benefits you have when you're in ZAL. The obvious, when you come in there, there's large research infrastructures. There is a future industrial line of Airbus with huge fuselage barrels with large robots which do Industry 4.0 experiments. And if you're a startup and want to develop some algorithms for the robots, you don't need to buy your own fuselage and your own robot. You just go there, make an agreement with the owners of the infrastructure and work there together. So it's very efficient to work together there. And it's also very important to be in dialogue, actually. So, actually the canteen might be one of the most relevant things in the ZAL, because you just meet the people, you sit there, you talk to the people, and over time you build a lot of trust. And if you come up with a new idea, the people will honestly tell you if it's a good or bad idea. Because often if you don't have this close relation, you come up with a new crazy idea, often you hear, oh, that's interesting, maybe come back in a half a year when you have worked on this a bit more. And here you seldomly hear this. They said either it's crap or it's brilliant, but it's never the polite answer. It's the technically correct answer you get. And for this you need trust, and this is what we have in ZAL. So we are together, we meet the people, we know whom to ask, and they will usually reply.
That sounds great. Yeah.
Yeah.
So you pitch while you eat. So Björn, what do you do at DLR to attract young talents?
Well, I think what works best to attract young talents is to have exciting topics. So greening of aviation, but also cutting edge digital engineering, both are topics we're very lucky that many young engineers like to join us as PhD students. But it's quite important to have enough of them. So we start quite early. We have a very close collaboration with universities for research. It's important to have the direct contact with the professors, but also with the students. So we host a lot of master students, bachelor students. We are highly involved also in PhD education, do this ourselves, but also join other universities. And to a lower end, we are also active together with schools and pupils, so we invite them to do their internships with us, and also girls and boys days. And I think it's very important to quite early attract them, because the best scientists we can get, or best engineers we can get, are those which really love what they're doing, which are really passionate about what they're doing. So it can be that they were glider pilots, or they are glider pilots, or model planes. Can be that they've watched the movie Top Gun 14 times. Can be that they like computer coding. So there's always an aspect of the work what really do passionately and did as a hobby in the past, and now get paid to do their hobby. And that's the best way to have intrinsic, motivated employees, actually.
I think, Björn, thank you so much for sharing your insights with us today. And please make sure to check out our upcoming episodes. We're going to be talking to a range of scientists, engineers, educators, and business people, giving you more insights on how in Hamburg our community is working on sustainable aviation and making industry greener. And look forward to seeing you soon.
See you soon.
See you soon.